So last time, okay, were there other things? Any comments? So last time we have a quick recap. Before we move on. Right. So we spoke about the geometrical interpretation of covariant derivative. Basically, we show that you can have a different definition of the geodesic equation. As a path whose tangent vector is always parallel to itself. Right. And then we briefly discuss gradient, divergence, and curve. Which basically generalizes the thing that you're supposed to learn from the previous studies. And then we started the subject of today, which will be curvature. We started by asking the basic question of how do we know whether a space-time is curved? And we have not started to discuss it, but we have not really defined it properly. The concept of parallel transport, right? So we take a vector, we parallel, transport the vector. So we transport the vector along some path from point A to point B. There's always a path from any manifold which we can find. And we're transporting the vector while keeping it parallel to itself. I did not yet define it, I'm going to define it shortly. We're just taking the vector, basically I'm taking it with me and I keep it always parallel to itself. And intuitively, if we have a flat space-time, and regardless of which path we choose between A and B, if I take the vector and I carry it parallel to itself, and I get to B, I get the same vector. But for example, the surface of the Earth has a manifold, which we said is not flat, right? As opposed to what some people may argue. If I take a vector and I transport it parallel to itself from point A, let's say the equator A, to some point B, which will be, let's say, the North Pole, then the outcome does depend on the path that we choose. We take this path, I take a vector, transport it parallel to itself. When I get to the North Pole, I do nothing as far as I construct the vector, I just carry it with me as I walk along. If I choose another path, let's say this path, I carry the vector. So my friend takes this path with the vector parallel to itself. When she meets me at the North Pole, our vectors will no longer be the same vectors. They will be parallel, but they will be oriented in different directions. And none of us was cheating. Everyone was very carefully carrying the vector parallel to itself. Still, we got a different result because in non-flat space-time, the outcome of the parallel transport depends on the path. There is nothing we can do against it. All right, question before we move on. No, everything is clear? If at home homework. You have more homework today. I don't follow what you do or what you don't do with homework. I strongly urge you, first, of course, to be honest in the homework. Do it yourself. If you have any troubles, come and ask. Actually, to ask, you don't need to ask. If you don't do it yourself, you will pay a hard price for that. The price you will pay when you get to the exam. So, do yourself a big favor. If there are things you don't understand, learn it now. Okay? Good. Okay. So, if there are no further questions, then there are no questions at all. No questions, everything clear? So now let's do a proper definition. So how do we say that the vector is parallel transported? What does it mean, parallel transport? What the mathematical definition to this intuitive concept that I keep a vector and I transport it parallel to itself? What would be a mathematical definition?
That its values are the same, like if you look in the flat space.
What does it mean the values are the same? So I have a path, right? I have a path which I, so this is the curve which I mark is x mu of lambda, right? This is my path along the manifold. One thing of manifold, and I select the path, right, lambda, and I have x mu of lambda. Right, this is the path. Now what? It was a flat space, so it's not changing. What does it mean it's not changing?
The component.
The what?
The components will be the same.
Which is the derivative is
Just
zero,
regular.
right? So flat space time. We have a tensor T. T is a tensor. It will be a definition of a parallel transport. Keeping it constant. Along the path means what? Et over the lambda is what?
0.
Of course, dx mu over the lambda, dt over the x mu is equal to 0. So, it is not changed. That enables us to define a new concept, which is the covariant derivative along the path. So, fine. Covariant derivative along the path. Basically, D tries to fit already. Okay. So what? I'll call it D or D lambda. In many textbooks, actually, this is not a standard notation. Many textbooks will be D over small d lambda. It's simply the way it is. How will I define it?
Just change the regular derivative to covariant derivative.
So Vx mu over the lambda, covariant derivative. This is covariant derivative along a path. Okay. Go to the parallel transport. So parallel V
So variant derivative along the path
along the path x mu lambda. Oh, yeah, right. V over lambda. V. This is the standard notation. Mu is a what? What?
0.
Of course. That's right. This is the whatever. Dx sigma over d lambda. Lambda sigma v mu. Or if you want dx sigma over d lambda v mu semicolon sigma. Of course. What do we have here? The regular derivative, d v mu over lambda plus gamma mu sigma rho dx sigma over d lambda v rho is equal to 0. This is the parallel transport of a vector v. And if you want to do a parallel transport of any tensor t, the t over d lambda mu1 k mu1 well exactly the same idea. D x sigma over lambda and lambda sigma t mu1 k mu1 mu is equal to 0. For example, if you have one component t over lambda mu d t mu over lambda plus gamma mu doesn't matter sigma rho dx sigma over d lambda t. What do I have here? What did they say?
Mu upper index.
Think again. What's the upper index?
O.
O. The lower index?
Many.
What?
Me.
Which?
Need.
Mu. Right. And then what will be the next term? What will be the next term?
Gamma. The fact correction.
Plus or minus?
Minus. Max.
Minus. Very good. Minus what? Gamma. What do I have?
O sigma D.
Good. And then what?
D x sigma.
Over
Lambda.
lambda.
The
And
tensor.
then t
U upper index.
mu
And rho lower index.
and very good. Okay, that's clear. Same thing.
So.
Now these equations, all of them basically, right? These are called equations of parallel transfer. Equation of parallel transfer. And it's very simple, right? You just take the vector, transport it along a curve. Keeping it constant means that the derivative has to be 0. Makes sense.
So, can you explain again the definition for
essentially, you know, it's a think of it as an initial value problem. Question solves. If we have a path x mu of lambda, let's say we have a path which is defined by x mu of lambda. Right? What would be the tangent vector to the path? Right. Okay. Just be x mu over the lambda.
Okay.
What do I get if I put the tangent vector to the path inside the parallel transport equation? Instead of v, what equation do we get? Geodesic. Why? Is that a coincidence? No. Why not?
Because we saw you told us in the recap.
What?
You said in the recap.
Exactly. Geodesic is just the path that the tangent vector is parallel to itself. So it's not surprising at all. So there's a very close connection between this parallel transport and the geodesic equation. Right? If I just take the vector which is tangent to the path, I'll get back the geodesic equation. Okay? Make sense? Everything starts to connect together somehow. Slowly, we'll get there. Okay. Now we are at a position to define curvature. Questions? Open university. So, how am I going to define a curvature? Come on, you know the answer already. How do I know if a given space-time or a given manifold is flat or curved?
Just calculate what we just wrote, and if it's 0, it's flat.
Calculate what exactly? What should I calculate?
You should specify some path and calculate the derivative.
Unspecified path. And
Just
maybe a parallel transport of a vector.
yeah.
So, what happened? How do I know if this is flat or curved?
If the vector have changed.
How do I know?
We
The
compare
vector
it.
here and the vector. I cannot compare the vectors at
Take
different points.
another path.
Oh, I can have another curve. Right? Which is exactly what we did in the example of the Earth I gave you, right? So now I can calculate how the vector changes if it goes along this path, as it goes along that path. I can compare them,
Yes.
right? And if it's the same, then I know it's flat. If it's not, I know it's not flat. I can actually quantify how much the vector changed. Right? So this is the basic idea.
Isn't it possible for a curved space-time there exists like two paths, but special two paths that will give me the same vector at the end, but any other two paths will give me a different vector?
No. Because
Necessarily-
I'm going to set the path, of course, to be infinitesimally small path.
Okay.
Right? Right? Don't look at global properties, and look at only the local properties. And of course, you can have a curvature which is different at different points in space-time.
But if you look in a small region from your point, then it's gonna be like in flat space-time, because each manifold, if you look close enough,
Will not. Will not. We'll see. It's true that by definition of a manifold, right?
Yes.
In the vicinity of, if I get close enough to a point, it will approach Euclidean space-time, namely flat.
Yes.
approach is not the same as equal to. There will always be some small deviation, which we can capture by that. But the importance really is that we can do these things locally. We don't need to go to outer space or something. Okay, so let's do it. So we're going to say that the curvature is going to define by the tensor, which is known as the Riemann tensor. Another name is the curvature tensor. So we define by the Riemann tensor. Mind you, Riemann was a student of Gauss. It's a mathematician. And what we're going to see actually, I'll prove it to you that we're going to get this tensor from the affine connection and the derivative of the affine connection. Meaning that, how do we get the affine connection?
Derivative of the
From the metric. Which means that in fact everything is already given to us in the metric. Metric tells us everything we need to know. Let's see that. Like in principle, right? Example, right? Minkowski space-time metric is just eta, or the derivative of eta of 0. So obviously the curvature will give us a 0. Say at this point. Okay, so basically, let's go along this basic idea that we have. So what do? We start with a point, which is denoted by 0, 0. Then we select two directions. How do we select directions? By two vectors. Vectors and directions. So let's say, let's call this P. This will be A mu, and this will be B mu. And we're going to go in infinitesimal length, delta A. This will be delta A 0. This will be delta A 0. Now, of course, we go A, we go B, reach delta A. Now, in principle, what I can do two things, right, which are equivalent. I can even take a vector, starting here and going along this full circle, and see how much it changed. Or what I'm going to do, which is easier, is take my vector and go from 0, 0 to delta A, delta B along two paths. One is this path and the second is this path. Let's see how it changed. Just going to be easier. So we have a vector V. See, that we're going to transport it parallel to itself from 0, 0 to delta A, delta B. Then now there will be a tensor. Well, the difference here would be some delta V. Okay. Let's call it, to be precise, let's call it delta V rho. It should be, we have V sigma, this is a vector. So it should be linear in V sigma. Right? Fine. This is infinitesimal. So what can I tell about this change? So the change in delta V should be, since everything is infinitesimal, right? Then it should be proportional to delta A, proportional to delta B. Right? It should be linear in V, which means that there should be a tensor which has one upper index and one lower index. That is the meaning of a linear in V. So it should have something which is R rho sigma, and it should also depend on the path that I choose, A and B. So it should be also A mu be new. I should have here a new and new. So we end up with a tensor. So R rho sigma mu nu. What rank tensor this is?
1, 3.
1, 3, right? It's a 1, 3, 10. Without doing anything, there is already one thing which we know about this tensor. That is what? If I switch the order in which I go, what will happen to delta V? It will be negative. So, right. So that means that if I, what does it mean switching the order? Means that I'm switching this to the last two indices, right? So it should be anti-symmetric in the last two indices. So I already know R rho sigma mu nu should be minus R rho sigma mu.
Can you repeat this about how you construct this equation?
Again, I'm not doing any calculations right now, I'm just thinking. I'm just doing I'm giving the arguments. So I'm looking at I'm taking the vector V sigma, and I'm transporting it from 0, 0 to delta A, delta B in two ways. And I look at the difference between them. Essentially, I look at the computation. And I'm asking, okay, this difference, what should it depend on? Right? So it should be linear in V sigma. By doubling V sigma, then the difference should be twice, which means it should have one upper and one lower index. It should depend directly on delta A and delta B, and how much I go. If I go further away. Why it's linear? Because everything is infinitesimal. And then it should depend on the direction which I take, which is given by these vectors A, mu, and B.
I can't get what is like how you like what is the vector?
What is what?
V.
Any vector.
That
This arbitrary vector which I take, and I just want to look at how this vector changes as I parallel transport it from 0, 0 to delta A, delta B along paths 1 and along paths B. That's it.
But why we decided to multiply all of the terms instead of subtracting, for example?
No,
Vector.
no. This is completely general. What I'm going to do, this is just a general argument, right? Heuristic argument. How do I expect V to change? What should delta V be, right? Delta V is V going path A minus V going path B. Right? So this is just based on some general arguments without doing any calculations here. I'm going to do it in 1 minute, so you can wait 1 minute and then listen. Yeah.
R is doesn't depend on the path, right? It's like an increasing property of the manifold.
It will depend on the path. I mean, how much it changes depends on the path I choose, of course. You said it, right?
No.
If I go through different paths, I will see different changes.
No, that's okay, but I think I don't know. I see it like
You'll see it is at the end of the day, you'll see that this is an intrinsic property of make a separation. Delta V is the change in V, which depends on the path. The tensor R, right, which tells us how much the change will be when we're going along a certain path, depends on the properties of the manifold.
Okay.
Right? The path is set by A and B.
Okay.
If I choose a different path, meaning I will choose different A and B, then I will get, of course, different change.
But R will be the same.
R will be the same
Okay.
at the given point. Right? Everything is infinitesimal. Okay. So what we're really going to do now, we're going to calculate this change. What we're really going to do is to look at the commutator of the two covariant derivatives. We look at the commutator of the two covariant derivatives of the parallel transport along curves. Which is essentially the same thing as what we have here. So put it for the moment and we see that. Okay, so let's say we have a vector field V rho, change from sigma to rho, and we look at the covariant derivative, so nabla nu V rho. V rho nu. Which is here because I need more space. Nabla mu of what we have dv rho over dx mu minus plus gamma rho mu sigma v sigma. Okay. Now, what we have here is what this is a tensor. What rank? 1, 1, right? So I have to have now one with a plus and one with a minus. Okay? So that is d over dx mu of dv rho over dx mu plus gamma rho mu sigma v sigma. And now I'll have with the plus one, so plus gamma rho mu sigma. I'll have the dv sigma over dx mu plus gamma sigma mu lambda, right? This is the mu replaced with a sigma, right? And then with a minus gamma lambda mu dv rho over dx lambda plus gamma rho lambda sigma bc. Okay, so now let's open it. I'll move back here because I'm going to need to now take the derivative here. So I have a d x mu dx mu v rho, so I just write d mu v rho plus I have to take the derivative here, so plus d mu gamma rho mu sigma v sigma plus gamma rho mu sigma d mu v sigma. That is what I have from this one. And then I just expand these terms. So I have plus gamma rho mu sigma d mu v sigma plus gamma rho mu sigma d mu v sigma. Here. Sigma, that's fine. These are these two. Again, 1, 2, 3, that comes from here, plus gamma. That, I don't need that. Just need to like that, so plus gamma rho mu sigma v sigma plus gamma rho mu sigma lambda, and then the minus gamma lambda mu d lambda d rho minus gamma lambda mu gamma rho gamma sigma. I mean, lengthy and annoying, but very much straightforward. Just follow the rule. That's what you do. Now we want to take the commutator. Take that and subtract minus the same as mu exchange. What happens when we subtract the terms of mu exchange? These terms go away. Mu and mu exchange. This term goes away. This term goes away. Now these two, again, when I exchange mu and mu, they interchange with themselves, so they also cancel out. So we are finally, what we get is that commutator of lambda mu and lambda mu of v rho is what we have here. d mu gamma rho mu sigma minus d mu gamma rho mu sigma plus 2 gammas with some linear change. So plus gamma rho mu sigma. I change the sigma here to a lambda. Okay, slightly change that. So this will be a lambda. And this is a sigma. Gamma rho mu lambda gamma lambda mu sigma minus gamma rho mu lambda gamma lambda mu sigma times v sigma. Okay. A little bit of an annoying algebra, but pretty much straightforward. There's nothing really different. So overall, this is the tensor that we want. So we write down W commutator W nu. V rho is R rho sigma mu nu V sigma, where the Riemann tensor R rho sigma mu nu is d mu gamma rho mu sigma minus d mu gamma rho mu sigma plus gamma rho mu lambda gamma lambda mu sigma minus gamma rho mu lambda gamma lambda mu sigma. Okay, we just write it. Questions about the derivation? Everybody is so shocked with these. So we did not exactly prove that this is what we get for delta V, but it is really. It's pretty straightforward to show that. So I just leave it for you to show that. Another thing which is more mathematical, right? We take the commutator, commutator basically is a differential operator, right? Take the derivatives. We end up with what we get is a linear change in here. But it is what it is. So, yes.
קוראים לו גם טנזור עקמומיות או שזה טנזור אחר?
It's a curvature tensor, a derivative tensor. It's the same, two names for the same tensor. It's a tensor acronym. There is some conspiracy here. You can see. I mean, this is not a tensor. Show that. Gamma is not a tensor. Derivative of gamma is not a tensor. But, you know, this is obviously is a tensor, which we can see it from here. The way we derived it, obviously this is a tensor. So we take some combination of quantities that are not tensors and their derivatives, and conspiracy they end up to be a tensor.
Is there something hidden that make it to be like this? Hidden
Well, again, there is a quite deep meaning here. Remember what I told you. At the end of the day, right, gamma we got from the metric tensor and the derivative. Here you can see that we get the Riemann tensor from gammas and the derivative of gammas. So essentially, if we know the metric tensor, G, we have all the information we need to calculate the Riemann tensor. Although it's quite a non-trivial calculation. Get gamma and it's not that straightforward. Another thing that you can immediately see from this definition is the property, the first property of R that we already derived, which is anti-symmetry in the exchange of the last two indexes, right? If we change mu and mu, you can see from here that we change the sign. So it's obvious from the definition that this property exists. If we want to look at the change of not the vector V but of any tensor T, how will it look like? If you want to take the commutator of the two derivatives of any tensor T, so if we have nabla rho, nabla sigma, or whatever tensor T, mu1, uk, mu1, mu L is equal to what? That should be pretty much straightforward for you right now. Right? R. Well, mu1, that would be lambda rho sigma T lambda u2 uk mu1 mu L plus R u2 lambda rho sigma T mu1 lambda 3 uk mu1 mu L. Then for every lower one there will be a -1 minus R lambda mu1 rho sigma T mu1 uk and then lambda u2 L minus R lambda mu2 rho sigma T mu1 uk and mu1 lambda 3 should be pretty much straightforward. So specifically, if we take the covariant derivative of a covariant commutator of a covariant vector, nabla rho nabla sigma of mu will be a what? Minus. rho sigma B lambda. So if the covariant vector vanishes, if the covariant derivative, if the curvature tensor is 0, what does it mean? They commute. Covariant derivatives commute. Now there is a mathematical theorem which I'm going to state it, but I don't feel that there is a need to prove it. The reason is I can't prove it, but it will take us the next 45 minutes or so to get the full proof. And I don't really feel a need to do that right now. So I'll just move one way, which is the simplest one. Which is the relation between the curvature tensor and the curvature of space. And the theorem goes like that. Those are writing down. The relation between the Riemann tensor and curvature of space. So the theorem goes like that. Necessary and sufficient condition. Necessary and sufficient condition for the metric G mu nu, say X, be equivalent to the Minkowski metric eta mu nu. R. What are the conditions?
Curvature tensor is 0.
Or that one, the components of the curvature tensor vanish everywhere. And the second condition is that the metric has 3 positive and 1 negative eigenvalue. G mu nu has 3 positive and 1 negative eigenvalues. Essentially, that says what we basically think of it, right? If R is 0 everywhere, all the components are 0, that means that the metric is fine. Basically, provided it has 3 positive and 1 negative. Necessary condition is very easy, so that I can do on the board right now in 21 minutes. So necessary, right? So if we have some coordinate system, let's see, sigma G mu nu is equal to 0. That means that gamma has to be 0, rho mu is equal to 0. And so D sigma gamma rho mu is equal to 0. So R rho sigma mu is equal to 0. But this is a tensorial equation. Being a tensorial equation. What about it? true in one coordinate system, true in any coordinate system. If true in one coordinate system, true in any coordinate system. Which means that the vanish of R is a necessary condition for the metric to be to the Gaussian equivalent. Now, sufficient is more tricky because that requires us to construct a set of basis vectors, which again I'm not going to do that because I can construct a set of basis vectors, but then I need to prove that they transform in the correct way. There is a theorem which is called Frobenius theorem. You can read about it. Frobenius theorem. The place that I found that they give the derivative is a textbook by Schutz, but it's not the textbook that I recommended. It's a slightly more advanced level textbook. It's called Geometrical Methods for Physicists or something like that. So this is C. By Schutz. It's called Geometrical Method for Physicists. Something like that, for the full proof. So I'm giving you a little bit of, giving myself a little bit of easy life by not providing you the proof, but again, I think it's. Okay. I don't like you to believe me in general, but this time I take a shortcut for myself because I feel that it will be not so much cost effective spending 1 hour making a proof, which will be mainly mathematical, and apart from proving it, will not give you anything else related to the course. So yeah, that is the theory. Questions?
There is physics here. I mean, by now we just spent a couple lectures about discussing how we can transport vectors, but how we can apply it for physics. I mean, we don't really transport vectors in physics, right?
What we do now, what I'm doing to solve
some equations, right?
What we're doing right. First, you're right. What we do right now is purely mathematical.
Yes.
What we're doing right now is defining what we mean by a curved space. And we said, remember, we were right that we will go back to the question of how does mass or energy acts to curve space-time. But before that, we are now answering the question of what do we mean by curved space, which is a purely mathematical question. So you're right that this lecture and possibly the next one, maybe only half of the next lecture on Sunday, will be still devoted to the full definition of properties of curved spaces. And then you'll see we're going to switch to back to physics when we'll finally answer this question, and then we'll see a lot of physics. So we're actually, if we look at the big picture, we're still have like 1 or 2 lectures which will be mainly mathematical in nature before we go to then the rest of the lecture will be nearly purely physics. There'll still be a lot of math, but there will be the center of mass of the course will be shifted from more mathematical to more physical. So if you're more into physics, then you have to wait a little bit more. Really, possibly we could start with that already on this coming Sunday, if not then next Thursday. All right, but yes, you're right that what we do here is, so far what we do is entirely mathematical, just the definition of a curvature. But you'll see that, of course, there is a lot of physical insight, which you don't yet see, but you'll see. More questions? next subject, which is necessary, is to look at some of the algebraic properties of the Riemann tensor. So it turns out that this tensor, I mean, it already looks quite ugly, right? And contains 4. So how many different components it has in 4 dimensions?
Just 64.
How many?
64.
You try again.
4 by 4 by 4 by 4.
Which is
196.
how many?
196.
Ah, yeah.
No?
Ah, yeah.
It's
256.
Yes.
256. So a total 200. I mean, this tensor has 256 independent components, which is quite a large number. Well, I just lied to you.
It's
They're not all independent,
because it's antisymmetric.
right? They're not all independent. In fact, this tensor. So first of all, like calculating 256 is quite a tedious and lengthy job. Of course, today you'll do it with a computer, but back in those days, there were no computers. I don't know what Riemann had to do, but fortunately, there are much less independent components because this tensor has to have a lot of there are plenty of relations, algebraic relations between the components of this tensor, and that is what we're going to do right now. So we want to study a little bit of algebraic properties of this tensor. Okay. So we said that what we're going to do now is completely general, namely, we're going to consider an n-dimensional space. N-dimensional space. Okay? So it's going to be completely general. It will be true for 4 dimensions as well as for any other number of dimensions. So start by saying in n-dimensional space there will be n to the 4 components. But in the last 2 indices, anti-symmetry. In the last 2 indices. So how many independent components there can be in the last 2 indices?
And to the second part, I suppose.
And to the 3D.
What?
Okay.
N dimensions,
Okay.
right? Because we have anti-symmetry. How many total independent components there can be in the last 2 indices? That would be n
Alpha.
squared.
N squared, half n squared.
Maybe? Not exactly.
I need to count the diagonal.
Then n minus 1 divided by 2. Right? Because the diagonal is
Okay.
right. Only have that. Right? Everything else, this has to be, sorry, you know, it's anti-symmetric, so it has to be 0. Right? And this has to be anti-symmetric from that. So you have n times n minus 1 divided by 2. Independent. There seems to be, there are several others relations, which we can study now, we're going to prove them now. Additional symmetries. for yourself. Think of it for yourself. It's the size of that track. Okay, additional symmetries. So to get additional symmetries, it's easiest to work with Riemann tensor with all lower indices, namely R rho sigma mu nu. If you can solve it by the end of the class, then come to me and solve it to you. You should be able to. Is G rho lambda R lambda sigma mu. Okay, so we just have to do it. R rho sigma mu is just G rho lambda. And then I'm just going to plug in the definition. So d mu is gamma lambda mu sigma minus d mu gamma lambda mu sigma plus G rho lambda gamma lambda mu alpha gamma alpha sigma nu minus gamma lambda alpha gamma alpha sigma nu. Okay, just plug in the definition of R. And now I'm just going to open it. I guess there's nothing much else I can do around. So, yeah, well, I'm actually going to open up the definition of gamma. Half G and half times gamma. So, you're going to get this is equal to 1/2 G rho lambda d mu G lambda tau. D mu G sigma tau plus first step in the first one, so it will be G lambda tau, and then I'll just take the derivative of everything in the center. So d mu G sigma tau plus d mu D sigma G tau mu minus d mu D tau G mu sigma minus d mu G sigma tau minus d mu D sigma G tau mu minus plus d mu D tau G mu sigma. That is, I expanded the two gammas here and I just took the G lambda tau outside and then just took the derivative inside. Plus now I take the derivative of inverse G, so plus 1/2 G rho lambda d mu G lambda tau d mu G sigma tau plus d sigma G tau nu minus d tau G mu sigma minus 1/2 G rho lambda d nu G lambda tau d nu G sigma tau plus d sigma G tau mu minus d tau G mu sigma. And then plus the last plus G rho lambda gamma lambda mu alpha gamma alpha sigma nu minus gamma lambda mu alpha gamma alpha sigma. Lovely.
Plug in.
I just expanded the definition of gamma.
Yeah,
That's
but
everything I did.
You
already
also-
need to it.
Yes.
What? No, partial derivatives commute. So if partial derivatives commute, then we get, let's see. This, so let's look at this line first. some things now start to cancel out. This gives us a delta rho tau. So for tau we can get a rho here. Tau we get a rho, G sigma rho. This is G sigma rho, so these two get cancelled out. This and this cancel out, and I have, that's it. So from here I'm left with, maybe I should do a different line. The first line, so from this line, get the 1/2 d mu d sigma g rho mu minus d mu d rho g mu sigma minus d mu d sigma g rho mu plus d mu d rho g mu sigma. Check it out. I wasn't cheating you too much. Now for these lines, for that line, I'm going to use the relation. We have here G rho lambda d mu G lambda tau is minus G lambda tau d mu G rho lambda, which we can write as a minus G lambda tau gamma eta mu rho G mu lambda plus gamma eta mu lambda G eta. Check this out. So for that, using that, if I can,
How can there are two mu lower index?
What?
There are two mu lower index. Maybe one of them should be beta.
means that I can find the lower index that should be an atom.
Yes. Okay.
Thank you. So from here we end up with minus gamma eta mu rho G eta lambda plus gamma eta mu lambda G eta rho times gamma lambda mu sigma plus gamma eta mu rho G eta lambda plus gamma eta mu lambda G eta rho times gamma lambda mu sigma plus whatever is left here G rho lambda gamma lambda mu alpha gamma alpha sigma nu minus gamma lambda mu alpha gamma alpha sigma. Okay. Yeah, I love this as much as you love it. Only I actually did all of that by myself to make sure it's right. And you will do it by yourself shortly. Homework, I guess, if you want. And then you end up that most of them cancel out. This one should cancel with this one. So minus here. And this one should cancel with this one. eventually be that our rho sigma mu is 1 half d mu d sigma g rho mu is d mu d rho g mu sigma minus d mu d sigma d rho mu plus d mu d rho g mu sigma plus g eta lambda minus gamma eta mu rho gamma lambda sigma mu plus gamma eta mu rho gamma lambda mu sigma. Yeah, I love it. This one is really good. But now that we've seen we've worked a little bit hard to derive all that, then we see a few more properties which can be directly derived, directly actually seen, so no need to derive anything from this definition, essentially, or expression, or so we have properties. One, symmetry under exchange of first and second pair of indexes. Rho sigma mu nu is R mu rho sigma. Okay, if I take these two, replace with that two, check it out, get the same result. Second, what happens if I exchange only a single index?
Anti-symmetry.
Anti-symmetry. Very good. So R anti-symmetry. R rho sigma mu is minus R sigma rho mu, which is minus R rho sigma mu. So anti-symmetry, which is plus R sigma rho mu. So anti-symmetry is just in the first pair, between the first or the second two indices. Okay, I cannot exchange all.
Why those properties?
Why what?
Why those כאילו למה התנאים האלה דברים? כאילו
Plug it in here. Just plug it here and just do it. See. There's nothing more that I can tell you about that at the moment. There's no real physics here. Anti-symmetry in exchange of indices in the first or second pairs. Then the 3 is cyclicity. Which means that there is an R rho sigma mu plus R rho cyclicity in the last 3 terms. Rho, do you know what is cyclicity? No. Let me just write it down. Mu sigma plus R rho mu sigma mu is equal to 0. So if I have some indices R0, 1, 2, 3, simplicity means plus R. No, I just changed this T3. 0, and then in a cyclic way, right? 2 goes to 1, 3 goes to 2, and 1 goes to 3. So 2, 3, 1 plus R0 and 3, 1, 2. Let's go cyclicity. Right, I don't know. You've never seen it
Like
before?
Jacobi identity, right? Or
It's related to the Jacobi identity, but it's not the same.
It's not the same. I mean, the logic.
Yeah, yeah, basically. I don't like the looks on your faces right now. On the one hand, I understand it. I mean, seeing all these derivatives, it's just. On the other hand, you know, I worked hard because I simply tell it to you, but I wanted actually to shoot. You can see and derive it for yourself. I'll post my lecture notes online, like today on Sunday, and you can actually follow them or just go to the textbooks. Again, I did not invent any of that myself. All right, questions about these properties? Now, one thing which we can do with tensors, remember, is contraction. What is contraction?
When we sum over one of the indices.
Identify one upper and one lower index. Right? So if we contract, contracting the first and third indexes, namely R lambda mu lambda mu, we get another tensor, which is R mu mu. There's only two indices, lower indices. This has a name. It's called a Ricci tensor. It's Italian. It's tricky, but it's actually Ricci. It's called the Ricci tensor. And in fact, that's the only independent contraction we can make. Everything else, and any other contractions that we can make, the Riemann tensor will end up with some dependence on the Ricci tensor because of all that properties.
What are applications?
What? We will see. One thing I can promise you right now: everything that I'm doing is needed. Trust me, there are plenty of other things that I could put in the GR that sometimes people put in standard GR textbook or standard GR courses, which I omit because they are not necessary. Everything here that I put is necessary. You can trust me on that, and we'll see that at the end of the course. Okay? This is the Ricci tensor. What we can say about the Ricci tensor is symmetric. What does it mean, a symmetric tensor? Is R and D. Now, if we have the, which is again follows directly from all the properties that we have. If we use the metric, we can contract the Ricci tensor, and we get what's known as the Ricci scalar. What does it mean if we use the metric? So if I do R mu mu, G mu mu, what do I get? This is R mu mu, which is simply called as R. This is known as the Ricci scalar. Both the Ricci tensor and the Ricci scalar are important for us. Don't know why, but we'll see. What?
What that represents, even in mathematical point of view, what is it decided for?
dimension of space. Okay? Essentially, they will tell you whether the space is curved or not. Remember that I said I consider the Earth like the surface of a sphere, to be a surface with a constant positive curvature. Yes. Essentially, that's what it means. Constant will be the Ricci scalar, and you can think of, imagine a manifold which has constant negative curvature. They look like a saddle. Then the Ricci scalar will get negatives. Actually, you're going to see that. And after I finish throwing at you all these maths, I'll give you a few examples, and you see it's not that horrible. Okay, it is horrible. There's no simple way of saying that, but okay. Again, you have to wait until Sunday, and then we'll see things. Hopefully, Sunday we'll wrap up this part, and then we'll see why this is good, what this is good for. Okay. Now, in the last few minutes that are left, after deriving these properties, I want to look at the number of independent components that the Riemann tensor really has in n-dimensional space. So let's look at that. Riemann tensor in n dimensions. So what do we have? We said that R mu nu, R rho sigma mu, anti-symmetric in the first two indexes. The question that I'm asking now basically is how many independent components does the Riemann tensor have? Okay? It's anti-symmetric in the first two indexes and the last two indexes. And symmetric under interchange of these two curves. Symmetric under interchange of the two curves. Right? Which we have here. So we can think of it. If we have a symmetric matrix of M by M, we can think of it as R, M, M. M symmetric matrix. Which is M by M. How many independent indices does it have?
M squared divided by
M multiplied by M minus 1 divided by
Symmetric. If it's symmetric,
M
Plus.
minus 1 power of 2.
if I have a symmetric M by M matrix, how many independent components does it have?
Yeah.
M minus
N plus 1
M plus 1 divided by 2. Right?
Right.
Now each one of these M's I can consider by itself as an anti-symmetric N by N matrix. So an anti-symmetric N by N matrix, how many components does it have?
N minus 1.
N times N minus 1 over 2. antisymmetric. Right. So total number of independent indices we have is 1/2 times 1/2 n minus 1 times 1/2 n minus 1 plus 1. So total number of independent indices. So if you open up the parentheses, you end up with 1/8 of n to the 4 minus 2n cubed plus 3n squared minus 2n. It's still a big number, but much less than n to the 4 we had previously. That's not the end of it. So we made use of that. We did not make use of the simplicity yet. What is simplicity? It means that the total anti-symmetric part has to vanish. Right? I don't know if you've seen that. Paste that one. So cyclicity. R is the definition. R mu by rho sigma mu with square brackets is equal to 0. Have you seen that before? Or not? No. Okay, so if I have, let's say, T mu sigma, mu rho sigma, it's copying from what I have, it's 1/6. By definition, it's 1/6. All the permutation divided by 1/6. This will be a T mu rho sigma minus T mu rho nu sigma plus T rho mu sigma minus T mu rho sigma plus T mu rho mu sigma minus T rho nu sigma. Basically, what I do, I take the Levitz-Civita tensor, so I don't touch the last one, and then for every permutation, I multiply by the Levitz-Civita tensor. Okay, so everything mu rho will give me a plus. I do one permutation, I get the minus. So mu rho mu, 2 ones, I get the plus, 3 ones a minus, etc. And then I go over all the permutations. Sigma I don't touch. It stays in the same place. Right, that's called totally antisymmetric. So how many constraints does this equation give us? Can have antisymmetric part. So the number of constraints. Don't see that right away. It should be n minus 1, n minus 2, n minus 3 divided by 4 factorial. That's constraints. I guess this is something hard to think a little bit. You've seen combinatorics, right? That's exactly that. So I'll take it for a second. So total, we're going to have, so overall, we have 1/8 n to the 4 minus 2n cubed plus 3n squared minus 2n minus 1 over 24 n minus 1 n minus 2 n minus 3, which is equal to 1 over 12 n squared minus 1. This is the number of independent components the Riemann tensor have has in n-dimensional space. at 4 dimensions, how many independent components do we have?
20.
20. In 1 dimension?
0.
0. Hey, how can you do? It's a 1-dimensional space.
No, it's not.
Yes, it is. It's a 1-dimensional space. Right? Can it be curved? No. Because from the point of view of an ant, it is sitting here. This is not curved, it's just going either this direction or this direction.
Okay.
No curvature of 1-dimensional space. What you think of it is curved because it's 10 dimensions. But if you are stuck to that 1 dimension, it's not curved. What about 2 dimensions?
It's curved.
What about 2 dimensions? How many independent components?
1.
1? 1. Richie? Scalar? Right, 1 component is a scalar. Right? Okay. Okay, I think this may be a good time to stop here. There's one more thing that we need to go, and then there'll be, but it's pretty short, so, and then there will be like a few examples of what to do. You get a feeling of that. And then we move to do physics. So Sunday is going to be quite I hope very interesting to you. Very important lecture. Any more questions before we go home? Okay, so we'll get a new problem set, so you can maybe think of that. And I know today was one of the more algebraic, I would say, lectures we had. Again, it's just following the indexes. I don't see that as something which is conceptually new. I think you get an important result, so there was a reason why I spent 2 hours deriving that, but there is nothing which is really conceptual. So if you get confused, which is definitely possible, make sure that you just follow everything and you see that I didn't mix up all the indexes. Highly unlikely, because I told you in previous years I actually asked students to check out if I made any mistake, and nobody found anything in the last few years, so I just thought that's it. So it's highly unlikely that you'll find something, but always good. So go over, check out, and see that everything works out and you understand all this theory. Right? And at the end of the day, this is algebra, it's not so much physics. Physics will come on Sunday. So have a nice and quiet weekend, and see you all on Sunday morning.
Thank you.
Thank you.